In this video, I want to go over one of the biggest application of Gauss's law that you will be seeing in this class, and that has to do with figuring out the electric field due to conducting and insulating spheres. So first, I do have to remind you as to what the definition between a conductor and an insulator is, just in terms of electric field and charge. So this is going to be a summary of what we're going to be going over in the video. Now, if I have a conducting sphere, the charge is going to be on its surface only. So there is no charge inside of the conductor. And that's something that you do have to either memorize, but you can also understand how it works physically. You need to know that in a conducting sphere, the charge is on the surface. If there's no charge inside, like we saw from Gauss's law, no charge inside means no electric field on the inside. So E is equal to 0 on the inside. And that is represented here in this graph, where on the y-axis, we have the electric field. And here, when little r, is just the distance from the center to any point, just radially outwards. So if I am, for instance, here, this point is less than capital R, which is the radius, so I'm inside my sphere, I have an electric field of 0. Now, when little r is equal to big R, so when I am pointing right here, so my little r that I'm drawing has magnitude big R, that means I'm on the surface here. Suddenly, my electric field jumps to its maximum because this is where I have all of my charge. So what I mean by that is if I put a positive charge right here, it is going to feel a lot of repulsion. Its force is going to be pretty strong, pushing it away. Right? Versus if I have a little positive charge down here, this again, R is just how far away from the center is my little charge. Well, it's not going to feel as big of a force as the one down here, right? So that's what this graph is showing. It's showing that the further away you are, the less and less electric field there is. At some point, there's going to be essentially no electric field. I can also write this out mathematically. So I'm saying in the inside of my conductor, there is no electric field. When I'm outside my conductor, this is my electric field, and we've seen this equation before. So Q over 4 pi epsilon naught R squared. This is very different, however, compared to an insulator. In an insulator, there is charge inside, and the charge is spread out uniformly. That means that if I were to, let's say, ask you what the electric field is at this point here, well, there is going to be an electric field. And we're going to figure out how to calculate that. So for any point in space, what the electric field is. Now, the electric field is going to start out at 0. By that, I mean, what if I were to ask you, what is the electric field at this point exactly at the center? Well, I'm saying the radius of the little circle I draw here is 0. So that's like a 0-dimensional point. Like there's no charge inside the center exactly. So my electric field starts out as nothing. And then the further and further away I go from the center of my insulating sphere, the more electric field there is. We're going to see this explicitly in the coming problems, but that means that if I have a positive charge here, it's going to feel more force than the positive charge that is down here closer to the center. Now this is true up until this point here, where little r is equal to R. That means this electric field increases up until the point where I reach the surface. Because then when I exit and I ask you what's the electric field down here, well, it's going to be less. The magnitude of the electric field is going to be lower than down here because I'm going further and further away from my insulating sphere. So there's going to be less electric field lines. And that, again, is going to decrease as such. So here, when we're inside of the sphere, my electric field is going to be this. Now I'm going to go over where we get this equation from. And then when we're outside, again, we're going to have the same equation before, Q over 4 pi epsilon naught over R squared. All right, so we're going to start this off by just having an insulating sphere like this. And we have charge that's uniformly distributed throughout it. And the first thing you might be asked is to figure out what is the charge enclosed for a Gaussian surface of r is less than r. So by that, I mean if I have a center point here and my sphere has a radius r, and I were to ask you how much charge is enclosed in a smaller circle that is centered, about the same center, and this has radius little r, how much charge is inside here? So how much charge is enclosed in here if I tell you how much charge is enclosed in the entire thing? Here we don't even have to use Gauss's law. This is just going to be some pretty basic math. So it's going to be Q in, so Q inside my little pink sphere. Remember, these are spheres, not circles, is equal to, well, what is the total charge times VR, so what's the volume of my small sphere, divided by V capital R, what's the volume of my big sphere. So this is really saying, well, okay, like how big is this volume compared to the outside volume? So I can write that in. So V of little r is going to be equal to 4/3 pi r cubed, that's just the volume of my sphere, divided by 4/3 pi capital R cubed. And remember, this is times Q total. So then I see that Q in is equal to Q total R to the 3 divided by capital R to the 3. And this is important to figure out because we're going to be using this when we are solving Gauss's law. So I can erase everything else. And that's the first part of the question. Now, the second part of the question asks us to find the electric field at point R when R is less than capital R. They're asking us now to figure out what is the electric field along this radius here. So because we know the charge is distributed uniformly, the electric field at any of these positions here that I'm drawing right now, it's going to be the same. Like it's going to have the same magnitude, and it's all going to be pointing radially outwards from the center. So that's going to be very useful because if we remember, this is Gauss's law, where E dot dA is equal to Q in over epsilon naught. So already we see why we need Q in. And then for the rest of the equation, we're going to have to essentially explain why we don't have to do this whole surface integral explicitly. Now, the first thing we know is that E, the vector, so the electric field vector, like I said, it's pointing this way. And as it turns out, it's always going to be pointing in the same direction as our area component. So our area component, it points radially outwards as well. So that means the cosine of the angle here between E and between dA, the cosine of the angle here is going to be equal to 0 degrees. So that means instead of saying E dA cos theta, cosine of theta is equal to 1. So then we get integral of E, the magnitude, times dA is equal to Q in over epsilon naught. Now the next good thing is that we know that the electric field is constant at every point in space along little r. So along this surface here, the electric field is going to be the same everywhere. So it doesn't change. So we can pull that out of the integral. Our integral is now E surface integral of dA is equal to Q in over epsilon naught. Now, whenever you see this, the surface integral of dA, well, this is just the surface area. Right? So this is the surface area, and we know what the surface area is for a sphere, and that is going to be equal to 4 pi little r squared. So here we can erase all of this stuff. And then we get that our equation becomes E times 4 pi r squared is equal to Q in, but we know what Q in is, which is Q total, times R3 over capital R3 divided by epsilon naught. So we went from having to solve a complicated surface integral to now really not having to solve anything and just having to move things around, because this is what we wanted. right? We want to figure out what the magnitude of the electric field is. So here we have Q total over 4 pi epsilon naught little r squared times r3 divided by r cubed. And we see these cancel out. And then the magnitude E is equal to Q total times r divided by 4 pi epsilon naught capital R3. And if you remember from the beginning of this video, this here is literally this equation, right? And this is valid when little r is less than big R. Essentially, this is an equation that allows us to know the electric field at literally any point in space within our instrument. And at this point x, I can figure out what the electric field is, because all I have to do is figure out, okay, how far is my point away from the center here? I can draw a circle like this, figure out, okay, how far away is it, figure out what little r is here, plug it into this equation, and that is what the electric field is going to be at that point in space. Now, the reason why this is not valid when I'm at r is larger than big R is as follows. So here, this is my insulating sphere. I'm just going to color that in pink. So this is my insulating sphere. And now I'm asking you to figure out, well, okay, what is the electric field at this point in space? So again, I'm going to draw my circle around it, like this. Should be concentric. That's still not concentric. And anyways, I'm going to draw from the center to here, and this is little r, and we can clearly see that little r is bigger than big R. Now, if I were to plug that into this equation here, well, I have to go back and remember what Q in is, right? Because if I rewrite my integral, my Gauss law, it's E dA, so E dot dA is equal to Q in over epsilon naught. Now, Q in here, in this case, it changed depending on how big my little r was, right? So if I was enclosing most of my insulator, a little bit of my insulator, where there's less charge, more charge, whatnot. But here, there is no charge in this empty space between it. So here, in this case, Q in is equal to Q total, right? Because there is no extra charge around here. So I'm going to go ahead and erase all this stuff, and we're going to figure out what the electric field is when a little r is larger than big R. So here, I still have the same equation, and the same things apply where I can take my E out, and I have dA, which is going to be equal to 4 pi r squared, right? Because this is the surface area of my Gaussian surface that has radius of little r. And this is going to be equal to Q in over epsilon naught. Q in here is just going to be Q total. So that means that my electric field is going to be equal to Q divided by 4 pi r squared epsilon naught. And this is what we have up here, right? So that is something you have to be a little bit careful of, is that you do have to use your brain when you're plugging things into these equations, and you have to remember what is Q in. And you can't just start making up charge for empty space. Now we can do the exact same method to figure out this equation here, because Q in is going to be the same. Because even if this here, this little pink guy, was an insulator, well, even if the charge is all on the outside, all of that charge is being enclosed by my Gaussian surface when I draw a Gaussian surface where little r is bigger than capital R. Okay, so that should be all for this problem.